everyone. In this video, I'm going to give a talk on our paper, Binary Matrix Completion under Diameter Constraints. My name is Tomohiro Koana, and I'm a PhD student from Technical University of Berlin. I remark that this work is mainly from my master's thesis, and this is joint work with Vincent, Froese, and Rolf Niedermeier. And you see a little sunflower because, as we will see later, our methods are going to exploit sunflower structures. As in the title, we study the matrix completion problem. And the matrix completion problem can be defined as follows in general. As input, we are given a matrix, say S, where some entries are unknown, or we say missing. And we need to complete S, or replace each missing entry by some character or number, such that certain properties are fulfilled. Matrix completion problem in general appears in many application domains. One is data science. In data science, probably the most famous example is the Netflix challenge. So in Netflix, you have a lot of movies, and there are users. And users can give a rating for the movies they watched. So we have naturally a matrix where each user is represented by a row, and each movie is represented by a column. So the entry becomes review score whenever they give a review. And when there is no review for some movie, then the entry is unknown or missing. And naturally, we would like to know whether or not a particular user is going to like the movie or not in advance. Another application domain is computer vision. Here we are given a picture or image where some pixels are missing or occluded. Then we would like to fill in those pixels to have a complete picture. Another application domain is computational biology, where we are given DNA sequences as rows. But like some parts of the sequences might be missing. Naturally, we would like to figure out what the missing entries are so that we have the complete sequences. And lastly, this matrix completion can be also model problems in coding theory. In coding theory, one might want to develop some strings where the pairwise distance is neither too far or neither too close. And this problem, as we shall see in the next slide, is modeled very closely by our problem. Depending on the properties we want to fulfill, there are many variants of matrix completion problem. Ganian et al. Studied a problem where we want to minimize the rank of the completed matrix, and they also studied a variant, its clustering variant. And Hermelin and Rosenberg studied a variant where we want to minimize the Hamming radius. And then in the follow-up work, we improved some of their results. And coming up next is this work, in which we want to fulfill some diameter constraints. Lastly, there's a work by Ivan et al., which is a clustering variant of the Hamming radius and Hamming diameter constraints. Let us define our problem more formally. So consider some matrix S with n rows and l columns. where each entry is 0, 1, or question mark. Here question mark represents a missing entry, and we say that a matrix is incomplete whenever it has a question mark. Additionally, as input, we are given alpha and beta that are integers. And the question is there a completion of S, or can we replace every question mark of S by 0 or 1 such that in the resulting matrix, that every pairwise distance between rows lies between alpha and beta. Show you an example. Here we are given a matrix S, incomplete matrix S, with 3 missing entries, which are marked by red. And S has 4 rows and 5 columns. And additionally, we are given alpha is equal to and beta is equal to 4. So to complete this matrix, observe that the first row and third row has distance exactly 4, excluding the first column. So this missing entry here must be replaced by 1 to match the third row. In a similar way, we can show that this missing entry must be replaced by 0 because the distance between the third row and the fourth row are 4, excluding the second column. And finally, with these 2 missing entries filled in order to fulfill the upper bound beta is equal to 4, we need to replace this missing entry by 0. And in fact, we can show that this matrix here also satisfies the lower bound, alpha is equal to 2. So this is the unique solution for this example. A fine-grained complexity of diameter matrix completion in terms of the distance bound, alpha and beta, as well as the maximum number of missing entries in any row. So when alpha and beta are constant, we have this figure where the green part shows the polynomial time solvable cases, and the red part shows that NP hard cases. In particular, we show that whenever alpha is equal to beta, or beta is equal to alpha, this line, and alpha and beta are constants, then diameter matrix completion can be solved in polynomial time. So now let me move on to another picture. On the other hand, when alpha and beta are part of the input, then we showed that even if alpha is equal to beta, so meaning that beta minus alpha is equal to 0, and when the number of missing entries is 3, the diameter matrix completion becomes NP hard. So in the remainder of my talk, I'm going to show part of the results. In particular, I'm going to focus on the 2 polynomial time solvable cases, namely when alpha is equal to 0 and beta is equal to 2, as well as when alpha and beta are both equal to 2. Before getting into details, let me explain how our algorithms work. So suppose that we are given input matrix S, and suppose that it has a hypothetical solution T, which is a completion of X with diameter constraints. Then we first analyze the structure of T. To do so, first we are going to represent the matrix T as a set system T. This actually allows us to use that data sunflower theorem, which I'm going to explain later, when the number of rows n or the number of columns L is sufficiently large. So with this structure at hand, we can develop an algorithm. So first, when either n or L is small, then we can basically solve the problem by brute force search. And then when the n or L is large, then we can reduce DMC to either 2-set or GF factor. Here the GF factor is some generalization of maximum matching, which can be solved in polynomial time. So we can represent a matrix T, which is a binary matrix with n rows and L columns, with n-1 sets, where the ith sets T sub I is defined as the set of column indices J, where the Tij and Tnj are different. So here's an example. So suppose that we are given this matrix T, then we focus on the last row here, and say like we wanted to compute T1. Then we look at the first row, and we see that between these two rows, they differ only on first and second column. So we have Ti is equal to 1, 2. And observe that when Tn, the nth row of T, and this family of sets are given, then we can reconstruct the set system calligraphy T. And one crucial observation is that whenever the matrix T has diameter at most beta, then also for this set system, every set in the set system T also has cardinality at most beta. Explain what the data sunflower theorem is. So suppose that F is a set family with M sets. We say that F is a weak delta system whenever its pairwise intersection size is some number mu, and we say that this number mu is an intersection size of F. So in this example, for instance, this 2, 3, 1, 3, 1, 2 is a weak delta system with intersection size 1. Like for instance, if you look at these two, the first two sets, then they only intersect on 3, which have size 1. And moreover, we say that F is a sunflower when we look at pairwise intersection. Then the pairwise intersections are equal to some set C. We call this set C the core of F. And in this example, for instance, well, this is a sunflower with a core 1, because every pairwise intersection is a singleton on 1. And this is called a sunflower because you can kind of draw it like sunflower, as you can see here. And what the data theorem says is that when you have a set family which is a 2 mu uniform, meaning that every set has size exactly 2 mu, and F is a weak delta system with intersection size mu, and moreover, if F is sufficiently large, then it basically states that F is a sunflower. We have seen the data theorem. Let me show the first step towards the polynomial time algorithm for the case alpha is equal to beta. So assume that alpha is some even number and let A be the half of alpha, and consider some matrix T where the pairwise distance is all equal to alpha. We claim that when there are sufficiently many rows, then the set system representation T is a sunflower. So to do so, we just need to show that the calligraphy T is an alpha uniform weak delta system with intersection size A. So observe that the cardinality of Ti for where the Ti is some set in the calligraphy T is equal to the distance between nth row of T and ith row of T, and this is by assumption equal to alpha, which shows that the calligraphy T is alpha uniform. Moreover, observe that the distance between Ti and Tj is equal to the cardinality of Ti plus cardinality of Tj minus 2 times intersection size between Ti and Tj. So plugging into the Ti and Tj is equal to alpha, we obtain that the intersection size between Ti and Tj is equal to A. So now that we have shown that calligraphy T is an alpha uniform weak delta system with intersection size A, we can use the data theorem, and we see that T is indeed a sunflower. So now let us develop the algorithm. So first, suppose that n is small. So in particular, we assume that n is less than a squared plus a plus 3. Then we can actually formulate diameter matrix completion as an ILP, basically with constant many variables. And whenever we have an ILP with constant number of variables, Lensstra's result says that such an ILP can be solved in linear time. Thus, we know that DMC can be solved in linear time. When n is sufficiently small. Now we look at the algorithm for the case when n is at least a squared plus a plus 3. To make the algorithm simple, we assume that both alpha and beta are equal to 2, and in addition, we assume that the sunflower T has empty core. So we reduce to bipartite matching. So first we introduce, for every row, we introduce a vertex except for the last row. So we have n minus 1 vertices, and then we introduce a vertex for every column. For the edge set, we add an edge between Ri and Cj if and only if jth column of S can be completed into some vector Tj, such that all entries except for the ith entry are distinct from the ith entry. And then we return yes if and only if there's a matching of size n-1, meaning that all vertices of R are saturated. Now let us look at one example. So suppose that we are given input matrix S, and for instance consider this entry here. Then this entry is between second row and first column, and there's an edge between C1 and R2, as you can see here. This is because the first column can be completed in such a way that the second row becomes distinct. Namely, it can be completed in such a way that if we complete it in this way, then the second row becomes distinct, making a petal of sunflower. On the other hand, if you look at entry here, there's no edge between C2 and R2. This is because in the next entry here, it has the same entry, so no matter how we complete the missing entries in the second column, this entry cannot become distinct from all other entries in this column. So now suppose that we have a solution for the matching. So now suppose that consider this red matched edges that satisfies all vertices of R. Then we can obtain a completion of S by, so whenever, for every column that is matched, we complete the corresponding column in such a way that for the matched entry becomes distinct. So for instance, if you look at the first column, so this entry here is distinct from all other entry in the same column. So this is basic idea for the algorithm. We've seen that when alpha and beta are both equal to 2, it can be reduced to matching, and hence it can be solved in polynomial time. I'm not going to get into the details. I'm going to explain what we found for the more general case. So when beta is at most alpha plus 1, meaning that beta is either equal to alpha plus 1 or beta is equal to alpha in general, we reduce to GF factor, which is more general than maximum matching. And this problem is known to be still polynomial time solvable. And we obtain the following. So when alpha is equal to beta, or beta is equal to alpha plus 1 for odd alpha, then the diameter matrix completion can be solved in NL times square root of n plus L. On the other hand, when beta is equal to alpha plus 1 and alpha is even, it can be solved in NL to the big O of alpha cubic time. So it seems that alpha is even case seems more difficult, and we were not able to improve this running time. Next, we develop a linear time algorithm for the case when alpha is equal to 0 and beta is equal to 2. First, we assume that every column has at least one 0 and at least one 1, because otherwise we can just delete the column. And so we analyze the structure of the hypothetical solution T, and suppose that the number of columns L is at least 5. We show that this matrix T basically has radius 1, meaning that there's a vector V of length L such that the distance from V and Ti is at most 1 for every row. This can be proved as follows. So first we represent the matrix T as a set family, and then we can show that this set family is a 2 uniform weak delta system with intersection size 1, and moreover we can show that the size of T is at least 4. This allows us to use the Desa's sunflower theorem, and we can conclude that the T is basically a sunflower. So suppose that we have a sunflower, say like 1, 2, 1, 3, 1, 4, then we can obtain a vector v, which is basically a vector where only the core is flipped. So this is the basic idea for the proof. And now let's design the algorithm. So suppose that L is at least 4, then we can solve the problem in linear time by basically brute force. So to do so, first we enumerate all set of vectors such that the pairwise distances are at most 2. This has 2 to the 2 to the L choices because there are 2 to the L vectors in here. And then we just check whether each row can be completed into one of the vector in the enumerated vector set. So when L is at most 4, the diameter matrix completion can be solved in linear time. So now, for developing linear time algorithm for alpha is equal to 0 and beta is equal to 2, we just need to solve the case when L is at least 5. And to do so, we use the fact that we use the known fact that the matrix completion into radius 1 can be solved in linear time by reducing to 2SAT. This was done in previous work, but for the sake of completeness, I'm just going to give you the idea of the reduction. So basically, we introduce a variable for every column, say xj, and the idea for xj is that this is set to true if and only if the jth column of the sort vector v is equal to 1. So clearly we are going to have at most L variables. And then for the clauses, we are going to add the following. For every row, we are going to introduce clauses to ensure that there's at most one deviation from that particular row. And such clauses, like we can encode such a constraint using big O of n clauses. So in total, we are going to have big O of n times L clauses. So since 2SAT can be solved in linear time, we have that the DMC, diameter matrix completion, can be also solved in linear time when alpha is equal to 0 and beta is equal to 2. With a bit more complicated analysis and some more work in the algorithm, we can also show that diameter matrix completion can be solved in n times L to the 4 time when alpha is equal to 0 and beta is equal to 3. On the other hand, when alpha is equal to 0 and beta is at least 4, diameter matrix completion becomes NP-hard. Well, this can be attributed to the fact that the matrix completion into radius at least 2 is NP-hard, as shown by Hermelin and Rosenberg. Now let me give you some concluding remarks for the talk. So we have introduced the problem matrix completion and diameter matrix completion and studied its computational complexity. For the tractable cases, we exploited Desar's sunflower theorem to develop an algorithm. In particular, we show that when alpha is equal to 0 and beta is equal to 3, so in this case, we can reduce to 2SAT to solve DMC in polynomial time. In a similar way, we also show that when alpha is equal to 2 and beta is equal to 3, after exploiting Desar's sunflower theorem, we reduced to a GF factor, and then we were able to solve it in polynomial time. This makes me wonder, what about the case when alpha is equal to 1 and beta is equal to 3? And maybe for this case, we need to reduce to something that is more general than 2-set and GF factor. I have no idea what that is. So I believe this is an interesting open question. But of course, like, we can also look at other open cases that we have in this picture. Like, what about the case when alpha is equal to 2 and beta is equal to 5, and so on. With that, I conclude my talk, and thank you for watching.